Convergence of a to infinity here, a to infinity, this is sin x upon x raised power m into dx, where a and m are both positive. Here a and m are positive, greater than 0. Both are positive. A and m are positive, greater than 0. Okay, so here we have to prove that this is convergent or is converges, right? If both a and m are positive, so that this function given, this integral given, the first kind of improper integral is convergent. If I take, let me take, if fx is equal to 1 upon x raised power m, 1 upon x raised power m, and gx equal to, let me take, sin x, or vice versa. If I take sin x as this fx, that is also possible, and the fx is sin x and gx is 1 upon x raised power n. So both the tables are either Abel's test or DIRICHLET'S test. Therefore, that we can prove this, that this function is convergent. Now this fx is monotonic decreasing. This is first test here. Here fx equal to 1 upon xn is monotonic, is monotonic decreasing for m greater than 0. If m is positive, m is greater than 1, let me take m greater than 1 here, or is positive. For m greater than 1, if I take here, m must be greater than 1, not 0. If it is 1.1, then the series is not going to happen. So this is monotonic decreasing function. So if I take m greater than 1, okay, so m greater than 1, that means m is equal to 1. Okay, this is 1.1. If m is 2, then 1 upon x square, it will be lesser value, lesser value, lesser value. In this case, this is monotonic decreasing function. So it is convergent for m greater than 1. Function is. This is convergent. So fx is convergent to a to infinity. But at x tend to infinity, the value will be 0. So this is 1 upon x raised power m into dx is convergent. Okay, as x tend to infinity, limit 1 upon x raised power m equal to 0. If I put here x tend to infinity, 1 upon infinity is 0. This is 0 here. At x tend to infinity, it is 0 here. That means this function is convergent. So fx is convergent, and sin x is, we know that integral sin x and gx, a to infinity sin x dx is equal to, if I integrate it, it will be cos x, it will be cos alpha minus cos infinity. Or if I take epsilon tends to 0, let me take limit epsilon tends to 0, epsilon tends to infinity, let me take, it will be minus cos. So this alpha will be, lower limit will come first, cos alpha minus cos infinity, okay, which is greater than equal to 2. This is finite here, is finite, okay, is greater or equal to 2, so it is finite. This value is greater than equal to 2, it is finite. Therefore, the function is convergent. Therefore, or hence, it's bounded. You may say here it is bounded. The second function is bounded, it is convergent. Not on decreasing function it was. And second function is convergent. Hence a to infinity sin x upon x raised power n dx is convergent. Is convergent is convergent. Hence, this function is convergent. Sin x upon x raised power m dx is convergent. Okay, with the help of, if I take first function as monotonic decreasing, either this is first function or second function. So either by Dirichlet's theorem or by ABEL'S test. Here Dirichlet's theorem is applied because Dirichlet's first theorem, first function, this one. If I take Dirichlet's theorem, that first function is monotonic increasing, this is monotonic decreasing. This is first function I've taken fx. This is by Dirichlet's theorem. Hence by Dirichlet's test. Hence by Dirichlet's test. By Dirichlet's, Dirichlet's, and by Dirichlet's test, this multiplication of function, this one, a to infinity sin x upon x raised power m is convergent. This result, hence by, I have to write here, hence by Dirichlet's test, sin x upon x raised power m within limits a to infinity dx is convergent. Okay, so this is how the Dirichlet test has been proved. Okay, the first function is done with the help of Dirichlet's test. Now let me talk about the second question. Now the second question is to be solved. Let me apply one of the tests here in the second case. What is the second question? Let me talk about second question. What does it say? Now to show that a to infinity e raised power minus ax cos bx dx converges absolutely where a is positive. Let me talk about second question. Yes, so that a to infinity e raised power minus ax into cos bx dx. Okay, this is the function which we have to prove that is converges absolutely. It converges absolutely where a is positive. Where a is positive, let me take, is positive, or a is positive. This is one of the questions let me talk about. So here, if fx equal to, let me take, e raised power minus ax is monotonic decreasing function, let me take, is monotonic decreasing or is bounded. If I express that e raised power minus ax into x raised power mu, if I express this, okay, for x equal to, now here limit extend to a is positive here, a is greater than, so a to x, if I take x raised power mu, e raised power ax is x raised power mu divided by, if I take in the denominator, this is 1 plus ax whole square from factorial 2 and so on. So this will be equal to 0. Okay, because in this case when x tend to infinity, when at limit x tend to infinity, this value will be equal to 0. Okay, so which is finite value is 0, means finite value, not infinite, it's not infinity. So it is, but 1 upon infinity, if I take, it is 0. Okay, so on this will be cancelled off, so 1 upon, so only, okay, so this is infinity here, 1 upon infinity is 0, 1 upon 0, that means infinity. Yet if I put x equal to x tend to infinity, that means 1 upon 0. 1 upon 0. 0 will come in the numerator. This will be finite value. Hence limits a to infinity, e raised power minus ax dx is bounded and monotonic. This is monotonic decreasing function. Is monotonic decreasing function. Okay. Okay, for here mu greater than, for mu less than 0 or so less than 1 or greater than 1, greater or equal to 1, and even for mu less than 1. For that also, if less than 1, the function is convergent already. But in this case, if it is taken less or equal, doesn't matter, but this function will cancel out this x. In that case, in both the cases, the value will be 0. That means function is bounded or finite. And this first part is finite and bounded, so this is convergent here. Now let me talk about second part. What about cos x? Here, a to infinity cos x is, okay, a to infinity cos x dx in multiplication, cos of bx, okay, is what you call, now this value will be sin bx upon, this is sin bx upon b, sin bx upon b, okay, a to infinity here. Now this value will be, because within a to infinity, this value may be greater than or equal to 2. Okay, is because the value is greater or equal to 2 or less or equal to 2. It may be less or equal to 1 here. But if I add them, because this is sin a plus b, so because sometimes it is added, it may be again less or equal to 2 here, which is finite. This function value is absolutely finite. Is finite for a greater than 0 or a positive value and within the limits a to infinity. Maybe at infinity it is infinite undoubtedly because it is sin x, but within this limit we will have number of values which are finite value, but its value cannot be more than 2, which is less or equal to 2. For it is finite for a greater than 0. So in both the cases, for mu less or equal to 1 or mu greater than or equal to 1, okay, less or equal to 1 or greater than 1, the function is absolute, the value is absolute finite, is finite absolutely, is finite absolutely. Therefore, this whole function is converges absolutely. Okay, so therefore, a to infinity e raised power minus ax into cos bx dx converges absolutely. Okay, any converges absolutely. But the value for mu, otherwise what the process, if mu is greater than 1 or equal to 1, then function is divergent. But in this case, even if, because this mu will be cancelled out, mu may be greater than 1 or less than 1, doesn't matter, the value will be 0, that means finite value in this case. That is, converges absolutely in both cases, if mu is less or equal to 1 or greater than 1. In that case, in both the cases, the function is absolute. The function comes out to be finite value, okay? Finite value holding. That means function is convergent absolutely, okay? Because otherwise, what is the mu test? Mu test in the previous lecture also we discussed about what the mu test. When mu is less than 1, then function is convergent. But if mu is greater than 1 or equal to 1, then function is divergent. That is the situation we will discuss in one of the questions here. That process here also applied. Okay? Let me take next question now. What is the next question here? Now question number next. Now third question. What does the third question say? Let me talk about question number 3. So that 0 to 1, here it is 0 to 1 cos x upon x raised power n is divergent. This we have to prove here. Is divergent, okay, when n is greater than or equal to 1. Okay, so this is divergent here. This we have to prove. Alright, now this value, because this is 0 to 1, so at x equal to 1, or if I take that fx equal to, this is solution here we are doing. Solution. Let fx, the first function, is equal to 1 upon x raised power n. This is monotonic decreasing function. Sorry, what I'm doing, I'm sorry. This spelling down. This is monotonic decreasing function. Monotonic decreasing for x for n greater than 1, but here it is between 0 to 1, only less than 1. So at x equal to 0, this value will be infinity. So it is decreasing. Okay, but this limits are 0 to 1 only. Limits are not 0 to infinity. If it's 0 to infinity, then the function is monotonic decreasing. But undoubtedly the form is monotonic decreasing, but limit extend to 0, 1 upon x raised power n equal to infinity. But 1 upon 0, if I substitute for any value, it will be infinity, which is divergent. So the function is divergent. So this function limits 0 to 1, 1 upon x raised power n dx is divergent. Whenever the value doesn't exist, it is infinity, the function is divergent here. So this is divergent, this part is divergent. Even if cos x, okay, cosec x is greater than 1 or equal to 1 is greater than 1. Okay, while 0 to 1 cosec x, this is, let me take gx here. If I take gx, let me take first gx. While gx equal to cosec x is, okay, let me take limits. Limit extend to 0 to extend to 0, or within 0 to 1, let me take limits 0 to 1. 0 to 1 cosec x dx is greater than 1, greater or equal to 1, because cosec x integration is log of cos x plus cot x, but at 0 to 1 the value may be greater than 1 or equal to 1. It's okay, but because this function is there, a part of this is convergent or divergent, then the whole value will be divergent, the greater or equal to 1. But multiplication of these two functions, therefore 0 to 1 cosec x upon x raised power n dx is divergent. Okay, is divergent for n, here n greater than or equal to 1. Okay, is divergent. Is divergent for n greater or equal to 1. So it is divergent. Okay, here n greater or equal to means positive value. If I take n equal to 1, 2, 3 and so on, 1 upon x square, but because 0, at 0 it will be infinity. One of the values, if it is infinite, is not defined, then function is divergent. So this function, multiplication of this will be divergent here. This is question number 3 we have done. Now let me talk about question number 4. What does question number 4 say? That talk about that also. Okay, so question number 4. What does question number 4 say? Test the convergence of, okay, now this function is 0 to infinity. This is e raised power minus ax. It is sin x upon x into dx. Okay, test the convergence of this. We have to prove, test the convergence. Whether this function is convergent or convergence of this. Test the convergence of this function. Test the convergence. Let me talk about question number 4. Now in this case, if I take, this is by ABEL'S test, if I take, let fx is equal to e raised power minus ax. Okay, e raised power minus ax. No problem. If I take it is by ABEL'S test, then sin x dx. Let me take first sin x dx. If fx is the first function, fx is, let me take sin x upon x. Okay, and for limits, we know that 0 to x, sin x upon x dx is equal to 1. This is finite here. Why this is 1? Let me talk about 0 to x. Now, if I divide this into two parts, let me take. If I take 0 to infinity, sin x upon x into dx equal to, let me take 0 to x here, a function, or 0 to a, let me take 0 to a, this is sin x upon x into dx plus a to infinity, this is sin x upon x into dx. Now this we know from the limits of the function that is equal to 1 at 0. So at x equal to 0, limit x tend to 0, sin x upon x is equal to 1. If I do this with the help of, because at x is 0, at x is 0.0 is not defined indeterminate form. If I apply, okay, solve that, if I differentiate each numerator and denominator, this is cos x upon 1. So at x equal to 0, cos x is 1, sorry, cos 0 is 1, this is 1 only. Or this is, in case of definite integrals, we start limits and functions. In limits and functions, we know that this limit sin x upon x is equal to 1. Okay, this is known to us. So first part is 1. Now second part, in case of this a to infinity, this value will also be convergent. If I just solve it with the help of this question, so this is greater or equal to 1. So this is also finite here. This function will also be finite. A part of this, so therefore, this part is converges. It's convergent because this value is coming as finite value. Is finite. A part of this is finite here. Therefore, this is convergent. This part is convergent here. So 0 to infinity, sin x upon x dx is convergent. The second part of this, or first part if I take, is convergent. So by ABEL'S test, if I take, so this is convergent here, is convergent. Okay, so this part is convergent. This is also convergent here. If I just express this, the a to infinity, within this limit, a to infinity, this value is greater or equal to 2, positive value. So this is also finite. That we have already proved. This is convergent. The two parts both are finite here in this case. This part is finite. This is also finite. This function is convergent here. The part of this is convergent. One part is convergent for a greater or equal to 0, a positive value. Within 0 to infinity, this function is finite. So the second part is finite. What? E raised power minus a, that monotonic decreasing function. And second part, let me take. And gx equal to e raised power minus ax is monotonic decreasing. Is a monotonic decreasing function. Decreasing function. Okay, so this is bounded. This is bounded, or this value will exist. This is bounded or will exist. It is bounded and monotonic decreasing. The function, a part of this is bounded or is monotonic decreasing or increasing. In this case, it is decreasing. E raised power minus ax is decreasing function monotonic decreasing function. So this part is mountain decreasing, another part is convergent. The multiplication of these two will be convergent by ABEL'S test. Therefore, by ABEL'S test, we can now say, hence by ABEL'S test, hence by ABEL''s test, 0 to infinity, e raised power minus ax sin x upon x dx is convergent. Okay, now this function is convergent here. Okay, so this is what you call convergency of this function. Question number 4. Fourth we have done. Let me talk about the next question. This is the fifth one. What does the fifth question say? Let me check the question number 5 here. Okay, so question number 5. Now it is proved that, okay, this is from mu test, 0 to a, this is dx upon square root, this is square root a minus x dx. It says it's convergent. Now we know that with the help of mu test, if I take this is with the help of mu test, if I take, let me talk about 0 to a any function, and here it is x raised power mu, and this is fx here. This is mu x raised power mu. Okay, and fx dx. If both functions separately, okay, are infinite, or they are continuous infinitely. They are infinite functions for value 0. Let put 0 here. But if mu is greater than 0, let me talk about, this will be with the help of mu tens will be convergent if mu is less than 1. If mu is less than 1, for mu less than 1, this function will be convergent. This will be convergent for, let me take, for mu less than 1. This function will be convergent for mu less than 1 and will be divergent. This we have discussed in the mu test in the previous lecture series, and will be divergent for mu greater or equal to 1. In this case, we will talk about that. What is mu here? That I'll talk about. This will be divergent for mu greater or equal to 1. Now let me talk about this question here. So this function is for 0 to a. If I put here 0 extend to 0 here, limit extend to 0. Let me talk about, this is limit, or extend to a. If I take here, I am taking extend to 0, the lower limit. Okay, for that, let me talk about. So this is 1 upon under root a into a minus x will be what? And this is here x raised power half. So I have taken this. This is mu test here. Is the mu equal to half? So I have taken x raised power mu. Okay, this is x raised power mu here I have taken. If I extend to 0, okay, if I take, it will be equal to, finally we will have 1 upon, because extend to 0 if I put here, and 1 a raised power half, sorry, this is x raised power 0. I'm sorry, this is a raised power half here. If I take a raised power half, this is a raised power half here. Or, I'm sorry, if I extend to a, okay, so this is x raised power half only. Okay, so extend to 0. Before that, this value will be equal to 1 upon under root a. X tends to 0, this will be 1 upon a. I'm sorry, this you have to take here a tends to a raised power half here, not x raised power 0, because a tends to 0. I'm sorry, x tends to 0. It will be equal to 1 upon a square root a. Why? Because 1 half a under root 2, because this is half a minus x. So I'm just talking about a tends to 0. X tends to a, not a, x tends to 0 here, but this x tends to 0, and half a into half a square root half a, 1 half a cancelled out. This will be 1 upon half a, which is finite value. Is finite for mu. Here in place of a we can take a also. For mu is equal to half less than 1. This is finite here, 1 upon root a. Now in second case, if I take x tend to a negative and limit x tend to a here. Okay, so this is a raised for half, okay, upon a minus x here. This value will be what it will be, a raised for half upon under root a minus x. In this case, x tend to a. So this a minus a 0, but before that under root a cancelled out. A minus a 0 infinity. Okay, so in this case this value is convergent to divergent. What is question number? Test the convergence of, sorry, this one. Fifth question we are doing. Question number 5 is 0 to a dx upon x. Oh, this is x here. I'm sorry. What I'm doing here. Then it's okay. Sorry. This is x here, not. Then it is x. Now it's okay. X raised power half. I'm sorry. This is. No, this is okay. I'm sorry. This I took wrongly as a, but this is not a. This is x here. I'm sorry. This is now okay. This is now we can apply mu test here. So here x raised power half it must be. This is x raised power mu. Here mu is half. This value will comes out to be, for x tend to 0, this x half will be cancelled out. This will be only under root a, because x tend to 0 then. This is here.